Good morning everyone. So, the last class, this is where exactly we stopped, expectation of a discrete random variable, right. So, remember I told you probability distribution is something which is the best to know, but which is cannot be known, right. It is like the truth for a random variable, okay. For a random variable, if you ask me what is the ground truth, it is the probability distribution, but truth as usual is unknown. So, we will not know the probability distribution. Then can I estimate the probability distribution from data? Well, yes and no. If you want to estimate, you really need a large amount of data, and in biological engineering per se or biomedical engineering per se, the data is usually small or large, small or large. Small or large is a relative quantity. How do you define? Small compared to what? Large compared to what? Okay. Do you know what is a dimension of a data? High dimensional data, low dimensional data. Have you heard of this dimension? What is dimension of a data? Hearing does not mean XYZ is not, it is 3 dimensional. I am talking about 10 dimensional data. What is 10 dimensional data? 10 parameters, 10 variables. So, have you heard of this term? So, suppose I want to recognize a parrot. I want to recognize a parrot. How do you recognize? Color, shape, size. Good. Then voice, beak, claws. How many you have said? Somewhere 7, right? In fact, just to identify a bird, we are using 7 to 8 features. So, what is the dimensionality of the data here? 8 dimensional data, right. So, dimension is nothing but features of the data that we are used to represent or characterize this data itself. Now, what about in biomedical engineering? What is the dimensionality of the data? Suppose I have to characterize your gene, huh? How, why? What are the combinations that one gene, one person versus other person can have in terms of DNA sequence? It is literally we are talking about millions, 80 Cg. If I straighten the DNA, so huge that the combinations are millions. So, what is the dimensionality of the data we are talking about? Very high dimensions. Very high dimensional data, be it DNA, be it. So, to exactly pinpoint a fault in the body or a disease in the body or disease pathways in the body, is it one? Is it one feature? Myriads again, because there are many features. So, COVID when it started, what did they say? Very simple, that are symptoms, and not only that, they said it will only affect the lungs. Then what did they say? Is it just the lungs? People got heart attacks, right. Then they said it is coronary as well, heart as well it affects. Then neural issues, right. Then they said brain fogging. One virus has disrupted the entire system in multiple fashions, and it is not uniform. Nobody said sore throat does not mean COVID, loss of smell does not mean COVID, more of these features, right. So, typically we are talking about a high dimensional data in what? In biomedical engineering, and therefore, the data set appears smaller when you look at the dimensions. So, how do you say whether the data set is small or large? It is always with regard to the dimensionality of the data. If I have 1000 million features, and if I have 10,000 data points, is it small or large? Small. If I have one parameter, one feature, and if I have 10,000 data, is the data set good or bad? Small or large? Large. So, the data set, the size has to be always in relation with the dimensionality of the data itself. In biomedical engineering, you are always having high dimensional data, and therefore, how much ever amount of data you collect is always less. you understand, whereas in other domains it may be different, right. 10,000 images may be good for something, but 10,000 images of CT scan, is it a large data? No, not at all. Even for one single case, one single disease, it is not large. Why? Because underlying confounding factors are too many, right. An 18-year-old getting affected compared to a 45-year-old is too different. So, for a 45-year-old, will you have 10,000 samples? No, you will have 2-3, you are short, right. So, there are too many factors that biomedical engineering you always end up with small amount of data. This is something to be kept in mind very clearly. And so, what is the implication of it? What is the implication? You cannot estimate the probability distribution, forget it, that is not going to be possible. If somebody tells you that I will estimate the probability distribution of the data in a biomedical engineering field, it is only a laughing stock, it cannot be possible. It is very next to not impossible, because you need so much amount of data. Now then, should I give up? Because I know the best thing to characterize the experiment, a random experiment, is through its outcome is probability distribution. I cannot estimate it. Now should I give up? No, that is not the way mankind works. So I told you yesterday how to distinguish these two. Now imagine I cannot estimate this probability distribution, but what can I do? I can figure out parameters that characterize, or there I can figure out quantities that can characterize this distribution. What are the quantities? Mean, spread around the mean, the kurtosis, either data is more probability this side or more probable to the right hand side of the mean, right. How peak is the data with respect to the shoulders, right, all of those, that is kurtosis. So you can have what I call it as quantities that give you an idea about the distribution, and that is what the mean, variance, etc. does. Okay. Mean, variance, etc. or kurtosis, why is it important? It characterizes, these are quantities that characterizes the probability distribution of a random variable. If you know the probability distribution, forget this, all of this is useless, but you will not know the probability distribution, you cannot also estimate the probability distribution, and therefore I am coming up with quantities that will characterize the distribution. Is it clear? The fundamental understanding has to be clear. These things you will not get it in the book. Okay, these are the things, you know, you have to feel for it and then see why is the need. Now having said that, then obviously there will be two means. What are the two means? Two kinds of means. What is it? Arithmetic mean itself, two means will be there, sample and population. So this is, suppose I know the distribution, suppose I know this distribution, what is the true mean? True mean is a weighted average, basically a weighted average. So these are the numbers. How will you average this? How will you take an average of this? What is the center point for the first distribution? Will it be truly at 2.5? Will it be at 2.5? Where will it be? Skewed towards left. Why is it? Why are you weighing? Because that is event, that outcome 0 is likely to occur more times. So that has to be weighed accordingly. The value 0 is going to occur more number of times. The value 1 is going to occur second, right. So the average cannot be just the center point here. It should be weighted with your weight values, which is your probability values here. So what will be my center point now? X weighed with its probability values and summed up. And remember, I do not take divided by n, etc., because this is population and probability value is the weight. So summation x f of x or x p of x, and notice probability value is always within the range 0 to 1. So this will give you the true mean or population mean. This is nothing but my true mean or population. Now can I know this? Can I know the true mean? Can I know the truth? Why? Look at the formula. It is multiplied with probability distribution itself. Anyway, probability distribution is not known. So, true mean is also not known to you. True mean is also not known. Then why am I learning this? I will come up with a quantity that will estimate the true mean. So, I am going to come up with a quantity that is going to be a that is going to estimate the what? True mean, right. So, what is that quantity that will estimate the true mean? So, this is true mean. What is the quantity that will help, that will be used to estimate the true mean? Sample mean. What is the sample? So, sample mean should be an estimate of now what is the formula for sample mean? Now tell me, look at these two and tell me what are the assumptions am I even making? Is there somebody who could think slightly better? So what are the weights for x bar? What are the weights? What is the weight for x bar? It is equal, right. So all samples are equally weighed. So that means this is not the best estimate when there are weights. So there is also something called as weighted mean, right. Sample mean is one, weighted mean is another. You can weigh them if you know the weights. Where will you use it? Weighted mean? In reality, come on, that's even a black box. You are adding one more black box to it. Where is weighted mean becomes useful? In biomedical application. You have seen blood reports, right. What are the, how do you read a blood report? Basically what will be there? Parameter and what is the range for glucose, blood glucose? 80 to 120. Pressure will be the blood glucose, blood report 80 to 120. Fasting sugar, right, actually 80 to 110. Now they have changed, they keep reducing. And then what about ALT? What is ALT? Liver enzyme, ALT, AST, there are several of them, right. Their range, will it be big or small? There are some entities which are small, some ranges which are small, some ranges which are large, right. Yes or no? You have seen the blood report, some are large, some are small. Why? And even let us say, your biomedical, you should be telling me, that is okay. I will take a simple example. Let us say you use a thermometer to measure temperature, use a digital thermometer to measure temperature, okay. You use a thermal gun to read the temperature. Remember in COVID times everybody were using thermal gun. What is expected from a thermal gun? Will it be accurate or less accurate? Sound. How many of you think it is less accurate? It is less accurate. What does it give you? After when a person uses a thermal gun, what do they read? Do they read the absolute value? What is it? In the malls also they were using. Wow, what does a security guy see there? Green or red? That is all. That reading, absolute reading, as it has very high accuracy or very high weight? No. Can a thermal gun be used by a doctor to measure the exact temperature? Now you understand where the weights are, right. Not all sensors have the same equal weightages, okay. In X bar you are assuming all samples are equally weighed with 1 over n, but that need not be true. And when it comes to context, you may want to see, I give work to 2 people, do you expect that I will have same one to a PhD guy and one to a undergraduate or just joined intern? Do you expect that my expectations will be the same and my level of confidence will be the same for both people? Wait, right. So that is where we have weighted mean as well. Sample mean typically weighs every sample equally, okay. And what should be it? The sample mean should be an estimate of population mean. How do I go about doing it? Is this an estimate of population mean? Why can I not have sigma xi by n squared? Now the weight is 1 over n squared. Is it a problem? Is it a problem if I put weight as 1 over n square instead of n? Uniformly having the weightage to be 1 over n square instead of n. Is it an estimate of sample mean, population mean? You understand my question? X bar should be an estimate of true or population mean. How do I show that? This E stands for what? It is called as an expectation operator. Expectation operator is linear. So what do I mean by that? Can I take expectation of x bar? Can I take expectation of x bar? What is this? Is it possible? Can I take expectation of x bar? Yes or no? Why? You all understand? When do you take expectation? When it is a expectation of a constant is what? Expectation of a constant is, what is there to expect anything about constant? Expectation of 10 is what? 10. So expectation is useful for a random variable, right? Is x bar a random variable or a deterministic variable? Everybody clear with that? X bar is random variable. Why is it random? Is it because of n? Suppose if I fix n to be 10, is it still random or deterministic? Why? You take 10 samples, I take 10 samples, it will be different, period. So x bar is always a random variable. So can I take expectation of x bar? Can I do this? Can we compute what is it? This is nothing but expectation of summation of xi by n. 1 over n is constant, right? So I can take 1 over n outside. Clear? Now I told you expectation is a linear operator. What do I mean by that? Expectation of m into x plus y is what? If m is a constant, this is nothing but expectation of x plus y, m times expectation of x plus m times expectation of y. You all know what is linearity, right? Or should I explain you? You all know what is linearity, right? Transformation of a1 x1 plus a2 x2 is equals to transformation of a1 x1 plus transformation of a2 x2, right? That is what linearity is. So now when I say expectation is a linear operator, expectation of m into x plus y equals to expectation of mx plus expectation of my. Since expectation is a linear operator, what can I do? Summation and expectation can be interchanged. Now what is this? 1 over n summation of expectation of xi. What is expectation of xi? What is expectation of xi? You have above, what is expectation of xi? Mu, the population mean, right? You have it above. So this is nothing but 1 over n times n mu. So expectation of x bar is what? Equals to mu. So on an average x bar goes to population mean. So x bar is an estimate of population mean, or x bar tends to population mean. When does it tend to population mean? When does x bar goes to mean mu? When does x bar goes to mu? This is where you have to be putting your efforts. When does x bar goes to mu? Put your thoughts. What is expectation operator? Expectation is nothing but summation of x into p of x. What is probability? Limit n tends to infinity n of a by n, frequentist approach. So, limit n tends to a, n of a by n tends to infinity n of a by n. So, when does x bar converge to go to mu? When n tends to infinity, very simple, because expectation of x bar is mu and expectation itself is nothing but multiplied with probability distribution, and probability is nothing but limit n tends to infinity n of a by n. So, the condition is when n is large or when is n tends to infinity, x bar tends to mu. Make sense? Clear everyone? Yes or no? Okay. So, this is about expectation of a random variable. Now, you know why x bar is a good estimator of, x bar is an estimator of mu under what conditions? When n is infinity, x bar will converge, will go to mu, and when and equally weighted, all the samples are here equally weight. Now, if you put 1 over n square, it will not converge. That is the reason why this formula is. You may be learning from 8th class or time unknown. The reason for x bar xi by n is simply because this is when this is what converges to mu as n tends to infinity, whereas if you put n square or n plus 1 or n plus, nothing will converge. Make sense?